Okay, so hello everyone. So last time we finished the section on LP spaces. Today we'll start by discussing some exercises on sheet 8 briefly, and then we start the next section. And I thought it might be good to just practice the essential supremum and infimum again. So I just chose the first exercise on in part A to discuss now. So X sigma mu is a measure space. And the question is, are the following statements true or false? And the first statement was the essential infimum of a function f depends on the chosen measure the second one was the following formula: essential infimum of f plus g is the same as S_inf f plus S_inf of g. C, if f is larger than 1 almost everywhere, then the essential supremum of f is also larger than 1. And finally, essential supremum of f plus g is less than or equal to S sub f plus S sub g. Okay, so this was exercise 1, part A. And I'll just write down the definitions of essential supremum and essential infimum again, because that's what we're going to be working with. So the essential supremum was defined as the infimum of the set of our xi in R such that f is less than or equal to xi almost everywhere. And the essential infimum, just analogously, the supremum of our xi such that f is greater or equal to xi almost everywhere. Okay. So let's start with part A. Essential infimum of f depends on the chosen measure mu. True or false? True. Why?
I mean, because of the definition of essential supremum, we are looking for the C such that f is less or equal than c almost everywhere, so
So which part in the definition
Almost
depends on the measure? Right. That's exactly right. So the first statement is true. As you said, because the definition of almost everywhere depends on the measure. If you change the measure, then this notion of almost everywhere changes, and the meaning of this whole thing changes. Okay. Okay, so any questions? Is this clear? Okay, so part B essentially says that the essential infimum is additive. Is this true or false?
False.
Why?
I was not able to find a counterexample, but I mean, I think that it's only greater or equal than the sum of the two essential infimum.
Okay, so you're right, it's false. But can anyone find a counterexample?
Yeah, if F and G have like disjoint supports,
Yes.
so like, I don't know, one's a square in one place and one's a square in the other. So like, one's the indicator function on 0 to 1, one's 1 to 2.
That should work. So I guess you want something like f to be such a function, and then g maybe this function, right?
Mm-hmm.
This should work, because then say their value is -1, then the essential infimum of f is -1. The essential infimum of g is also -1. So the right-hand side is -2. But on the left-hand side, if you take the sum of the two functions, it's just these two blue boxes, and the infimum of these is still -1. So we'd have -2 on the right-hand side and -1 on the left-hand side. So this would be a counterexample, yes. Everyone happy with this? Any questions? Okay, so then part C. If f is greater or equal to 1 almost everywhere, then the essential supremum is greater or equal to 1 almost everywhere. Greater or equal to 1. True or false?
True.
Yeah. Do you have a true?
If f is greater than equal to 1 almost everywhere, then the essential infimum is greater than equal to 1. Then the essential supremum is greater than equal to 1.
Can you, so yes, yes, that's correct. So it's, C is true. But, yeah, can we find an elementary proof of this that only uses the definition? Yeah?
If f is greater than or equal to 1 everywhere, then in particular it's greater than or equal to 1 almost everywhere.
Yes, but we're only assuming that it's greater or equal to 1 almost everywhere.
Oh, I missed almost, sorry. Yeah,
Okay.
that's it.
Yes, does anyone have an idea how we could prove this?
suppose f is less than 1 in an outset, and so the seal in the definition of essential supremum cannot be, has to be at least 1.
Yeah, that goes in the right direction. So yeah.
I mean, if I take something a little smaller than 1,
Yeah.
I cannot say that f is less or equal than 1 minus epsilon almost everywhere. Because
This should work. So let's try and write this down. Let's take some positive epsilon. Then the statement f less than or equal to 1 minus epsilon almost everywhere is false, right? If it's greater or equal to 1 almost everywhere, then the set of points where it's less than 1 has measure 0. So its complement can't have measure 0 as well, except when the measure is 0, but then everything is trivial. So this statement has to be false for every positive epsilon. But then this means, because this condition defines this set, right? This means that 1 minus epsilon is never in this set for any epsilon. Okay, but this means that the infimum of this set has to be larger than 1 minus epsilon. Right, because for no epsilon, there's an element of this set. Okay, but now on the left-hand side, there's just the definition of the essential supremum. And now we know that this holds for any positive epsilon. So we can send epsilon to 0. And get that the essential supremum has to be greater or equal to 1. And that's what we wanted to prove. Yeah?
I might have another way possibly, and that's if f is greater than or equal to 1 almost everywhere, then that means that its essential infimum has to be greater than or equal to 1, and the essential supremum is greater than or equal to the essential infimum.
Yeah.
So that in turn would be greater than or equal to 1.
Yeah, that works. That uses a little more gear because you're not doing it. It is not as elementary because you're not doing it from the definition, but it's correct. Yeah. Any questions about this type? Okay, so the last one. Essential supremum of f plus g is less than or equal to essential supremum of f plus essential supremum of g. Yeah, we know that equality is not true because by the same reasons as in this case. But now we have an inequality, so this could still be true. Is it true or is it false? True. Yeah. Yes, that's correct. Can you prove it?
If I take the right hand side, I know that is greater or equal than f plus g almost everywhere.
Okay, so yes, slowly. So we have f less than or equal to s sub f almost everywhere. That's because of the first exercise in part B. There, this was, you had to prove this. Yes, and if you use this.
And the same thing also for g. And then
Yes.
f plus g is less or equal than the sum of the two essentially.
Right, so just add these two inequalities.
Almost
Okay.
everywhere.
Almost everywhere. Okay.
And then, so the right hand side is an element of the set, the first set.
Yeah. So this right hand side, because f plus g is less than this almost everywhere, I can take this right hand side as a psi in this set,
Yeah.
with f replaced by f plus g. Okay.
And then the essential supremum of f plus g is the infimum, so has to be less.
Right.
equal.
Yeah, because the essential supremum is the infimum of that. We know that it has to be less than this right hand side. Yeah, and that's part D. So this is how you prove it. So I think we still have time to do one more exercise. We could do the first exercise of part B. I haven't prepared it because I didn't think this would be so fast. But I think it would be a good fit because we've used the first exercise of part B in this proof. So let's just do this one together and then continue the lecture. Okay, so we were given a measure space and a measurable function, and then let's just do one of the two. So prove f less than or equal to s sup of f almost everywhere. Okay, how do we do this? Okay, I think there was a hint, wasn't there? Yeah. So let's see if I can do this from the top of my head. So the essential supremum was defined as an infimum. So by definition of the infimum, there exists for every n there exists an element of this set such that S sup of f plus 1 over n is greater than xi. Right, I can always find an element of this set which is only slightly larger than the infimum. Yeah. So we have this. Because xi is in this set, we know that, let's call this xi n, right? Because it depends on n. For every n, there's a xi n. F is less than this xi n, almost everywhere, because xi n comes from this set. But now xi n is less than this. So f is less than S sup of f plus 1 over n, almost everywhere. Okay, but now now we can just let n go to infinity. There's a catch. So I was one step too fast, sorry. So we get this inequality almost everywhere, which means that for every n, there exists a null set E such that f is less than s. So f plus 1 over n on x minus e okay, but now this e depends on n. That's what I was just missing. So what we have to do is take the union of all these dn, then that's still a null set because it's a countable union of null sets. And f is less than s. So f plus 1 over n for all n on x minus this union of all the en. And now we can let n go to infinity because this null set does not depend on n anymore. And because this union is still a null set, this is satisfied almost everywhere. And that's the complete proof. Okay, so sorry if this was a little bit bumpy, but I had to improvise. Are there any questions about this exercise? Okay, so if there are no more questions, we start a new section in the lecture. So this is section 6 called Uniqueness Lemma and the Monotone Class Theorem. And in this section, we ask ourselves a natural question, namely, so this section will be, again, dealing with the abstract stuff about Sigma-algebras and measures and so on. So no integrals in this section. And we've seen sigma-algebras, we've seen sigma-algebras generated by certain sets and so on. And then in connection to measures, one question is quite natural, namely if we have a set X and some family of subsets, and now suppose we have two measures, mu1 and mu2, which agree on A. Then it's a natural question to ask whether one has mu1 equals mu2 on the sigma algebra generated by A. So in other words, if two measures agree on the generator of a sigma algebra, then do they also agree on the entire sigma algebra? And this is the question we'll study in this section. And I think today we should have an answer to that question. So to study this, yeah, we have to go back and define certain algebraic structures which are similar to sigma algebras, but slightly simpler. So the first definition is let X be a set, and let S be a subset of the power set of X, so a collection of subsets of S. Then first S is called a pi system. If on pi system on X, if S is closed under finite intersections. Okay, so this is simple. If you take the intersection of two elements of S and they're in S again, and this is always true, then S is called a pi system. And second, S is called a D system if the following things are satisfied. First, X is an element of S. Second, if two sets are in S and AB in S and A is a subset of B, then B minus A is in S again. And C, if we have an increasing sequence of sets, so S1, subset, S2, subset, and so on. If all these are increasing and elements of S, then the union of all the Sn is in S again. So if these three things are satisfied, then we call S a D system. similarly to sigma-algebras, we can define the D system generated by a set. So that's the next definition. If A is a collection of subsets of X, then the intersection of all D systems containing A is denoted D of A and it's again a D system. We're not going to prove this, but the proof of this is very easy. It's very similar to the case of sigma-algebras generated by a set. So yeah, the intersection of all D systems of a set is again a D system, and D of A is called the D system generated by A. And yeah, maybe let's write down the next lemma and then take the break. So the first thing we're going to prove in this section is lemma 6.3. No, actually, we can prove this now. This is short. If we have a set S subset P of X, then this is a sigma algebra if and only if S is both a pi system and a D system. Right, so here's the connection between these strange pi systems and D systems and the sigma algebras which we're used to. Namely, a set is a sigma algebra if and only if it's both a pi system and a D system. And the proof, so one direction is trivial, namely if S is the sigma algebra, then it's clear that it's a pi system and a D system. And that's trivial because if S is a sigma algebra, then what do we have to check? It has to be closed under finite intersections. We know that this is true for sigma algebras. This has to be verified. Yes, that's true for sigma algebras. This property is true for sigma algebras. We've seen all this earlier in the lecture. And of course, this is true for sigma algebras. So really, this is all follows from the stuff we proved in the first few sections about sigma algebras. So for this direction, there's nothing to prove. For the other direction, let S be both a pi system and a D system. And now we want to show that it's a sigma algebra, and again, many things are already satisfied. This one, for example. So the only thing we really need to prove is that S is closed under countable unions. So because that's not automatically satisfied. In the definition of a D system, we have closedness under increasing countable unions of increasing sets. But in the definition of sigma algebra, the sequence does not have to be increasing. So that's one thing we have to show. So, given any sequence of sets in S, we have to show that the union of these Sn is in S again. Okay, so we want to show that the union of these is in S again. We know that the union of an increasing sequence of elements of S is in S again. So let's just turn this sequence into an increasing sequence and use the fact that S is a D system. So let's write Sn prime. We've seen this trick a couple of times already. S prime to be the union of k equals 1 to n sk. Now the S prime are an increasing sequence of sets. Okay, and we have to check that these S prime are in S again. So we can see this if we write S prime as x minus the finite intersection from k equals 1 to n of the complements of sk. Because these complements of sk are in S again by this property B. So these are in S. And now the finite intersection of these is in S again, because S is a pi system, hence closed under finite intersections. And then it's a complement again, so we can use this again. So this entire right-hand side is in S. Okay, so these Sn prime that we defined are in S. But by definition, the Sn prime are an increasing sequence. So we have an increasing sequence of sets in S, and from property C, we know that their union is in S again. So the union of the Sn prime is in S, but the union of the Sn prime is equal to the union of all Sn, right? So this shows closeness under countable unions. And as I said, all the other assumptions of sigma-algebras are already satisfied automatically by these properties. So this ends the proof. So okay, nice. So any collection of subsets is a sigma algebra if and only if it's a pi system and a D system. And I think this is a good time to take the break. So let's continue 3:05. Yeah, we take 10 minutes break.
I just say yes, reference me.
I do. One issue, RB cannot be 20. RB can't be any greater than 5. Yeah, so we'll see, but that doesn't make any sense. Although I can see that randomly too. If I go, what was it, 5. It doesn't solve it.
Really?
What? Fubini?
You have to leave out a lemma for Carl to prove in the night. In fact, what I'll do is I'm going to bring in some gold paper. So write Fubini theorem on the gold thing. Just so we know how.
Some like German sausages on the piece. In the morning you wake up with Fubini's theorem. Maybe Christmas tree.
Started before Fubini mess. North of the house, which was staring.
Okay, so let's continue. So the next lemma is called Dynkin's lemma, and it says the following. If we start with the pi system and then take the D system generated by that, then the D system generated by that is still a pi system. So we don't ruin the pi system property by taking the D system generated by a set. And this implies that, well, if it's been a pi system before, then we take the D system generated by it, then it's both a D system and a pi system, so then D of A is a sigma algebra, as we've shown earlier. And in fact, this implies that then D of A has to be the sigma algebra generated by A. Because D of A contains A, and D of A is the smallest D system generated by A, and every sigma algebra is a D system, and yeah, that's why these two things have to be equal. That's why D of A has to be a subset of the sigma algebra generated by A. And because D of A is also a sigma algebra, it has to be a superset of the sigma algebra generated by A, and so they must be equal. So this is neat. This gives us a procedure for constructing sigma algebras, right? You start with a pi system, you take the D system generated by it, and you get a sigma algebra. And you don't just get any sigma algebra, you get the sigma algebra generated by A. Okay. And the proof has two stages, and it's a little involved. I'll try to make it as clear as possible. So the proof starts with proving the following claim. if we take an element A of A, then an S in D of A, then the intersection of A and S is again in D of A. Okay, so if we take an element of A and an element of D of A, then their intersection is in D of A again. And the proof of this claim goes as follows. We define a set D to be all S in D of A, such that for every A in A, one has the intersection of S with A is in D of A. Okay, so elements of D are defined by the property that if you take an element of D and you take the intersection with an element of A, then the result is in D of A. And now what we're going to show is that this set D is a D system. Okay, to show that D is a D system, we have to show three things. Right? The first one, X, the entire set, has to be an element of D. But that's clear, because if you take X and the intersection with any A, then this is the intersection of X and A is just A again, and that's in D of A because A was in this set A to begin with. So X in D is clear. The second one is, okay, the second property of D systems was if we take one set minus another set, then that has to be in the D system again. So more precisely, if S1, S2 are in D, and S1 is a subset of S2, then we have to show that S2 minus S1 is in D again. And S2 minus S1 being in D means we have to take the intersection with the set in A and then show that that's in D of A. So we have to take a set in A. So then for A in A, we have that S2 minus S1 cap A. Right, so now this has to be in D of A, because that's the condition for S2 minus S1 to be in D. Okay, so this is the same as S2 cap A minus S1 cap A, and now this is in D of A, and this is in D of A, because S1 and S2 were in D by assumption. So S1 being in D means the intersection of S1 with any element of A is in D of A. So because S1 was chosen from D, S1 cap A is in D of A. And the same for S2. So these two sets are in D of A. But D of A is a D system, so the difference between these two sets is again in D of A. So we know that this whole thing is in D of A. Okay, but this intersection being in D of A is precisely equivalent to S2 minus S1 being in D. Which is what we wanted to prove. Right, so the second property of D systems is satisfied. And the third we have to check is if we take an increasing sequence of sets in D, then the union of these has to be in D again. So we do a similar thing. We take a set from A and take the intersection, and then that has to be in D of A. So union n equals 1 to infinity of Sn cap A. For A in calligraphic A. Okay, so this has to be in D of A. So we can rewrite this as the union n from 1 to infinity Sn cap A in brackets. But now this Sn cap A is in D of A by the same reason as above, because the Sn came from D, and D was defined by the property that elements of D intersected with such an A is in D of A. So all of these are in D of A, and the sequence of these intersections is still an increasing sequence of sets. So because D of A is a D system, this union is in D of A again. Okay, so this proves the third property of D systems. So we've shown that D is a D system. Okay, but not only do we now know that D is a D system, but let's go back to the assumption. This collection of sets A was assumed to be a pi system. Pi system means it's closed under finite intersections. So, in particular, A is a subset of D. Right? A is a pi system, so this means if you take an element of A and take the intersection with another element of A, then that's in A again. And D was defined to be the set of elements for which if you take an element of A and take the intersection of the two, then that's in D of A. So every element of A satisfies this condition here. because A is a pi system, right? So this is the same as to say that A is a subset of D. Okay, but this means D is a D system and A is a subset of D, so D of A, the D system generated by A, has to be a subset of D as well, because D of A is the smallest D system that contains A. But now let's go back to the definition of D. D was defined to be all elements of D of A such that some condition holds. So by definition, D is a subset of D of A. So we get both inclusions between D of A and this calligraphic D. So they must be equal. And this proves the claim. Because D being equal to D of A is precisely this this implication here, right? The claim said that if we take an element of A, take an element of D of A, and take the intersection, then that's in D of A. So if D is equal to D of A, this means that every element of D of A has this property. And that's precisely what this claim means. Okay, so the claim is true.
How do you know the other inclusion? Say that D is equal to D of A?
From the definition of D, because D was defined to be all elements of D of A such that something holds. So it's by definition a subset of D of A. So this was the first step of the proof. And now comes the second step, which is almost identical. So to prove the lemma, it is sufficient to show that the following holds: E is equal to D of A, where E is defined as the set of all S in D of A, such that for every A in D of A, one has S cap A is an element of D of A. So this set E is, okay, first, by definition, it's a subset of D of A, right? Because it's the set of all elements in D of A such that something holds. So we know that from the start. Now, this set E looks very similar to that set D over there. The only difference between D and E is we have a D of A here, and we have A in the definition of D. So this condition that defines E is slightly more difficult to satisfy because this set here is larger. So something has to hold for every A in D of A rather than just for every A in A. Okay, and now I guess I have to explain this sentence. To prove the lemma, it is sufficient to show that this set E equals D of A? Well, the statement of the lemma was, if A is a pi system, then D of A is again a pi system. So we have to show that D of A is a pi system. D of A being a pi system means that D of A is closed under finite intersections. So D of A has to be closed under finite intersections. And now let's look at the definition of the set E. E is the set of all S in D of A such that the intersection of S with an element of D of A is again in D of A. So it's the set of all S in D of A for which the intersection with the set from D of A is again in D of A. So it's the set for which this condition that we want to have for a pi system is satisfied, more or less. So if this condition is satisfied for every S in D of A, then D of A is a pi system, right? But this is precisely the same as saying that E is equal to D of A, right? If this is satisfied for every S in D of A, this means that this whole set is equal to D of A. I hope that was clear. So all we have to show really is that this set E is equal to D of A. And we already have some experience in showing this because we've shown the same thing for a very similar set, namely D. And indeed the proof is very similar. So let's show that E is a D system. X is in E, that's clear again, because the intersection of X with any set from D of A is the same set again, and then this condition is trivial. Second, I can almost copy word for word from over there. If S1, S2 are in E, S1 is a subset of S2, and A is an element of now D of A, not A, then we do the same thing again. S2 minus S1 cap A is the same as S2 cap A minus S1 cap A. And now this first set is in D of A, the second set is in D of A. Why? Because S2 was a set in E, and if we take a set from E and take the intersection with an element from D of A, then that's again in D of A by the definition of this set E. So this intersection is in D of A again, and then the same is true for this intersection, and then for the difference between the two sets, because D of A is a D system, it's in D of A again. So this is in D of A, which means that S2 minus S1 is in E by definition of E. So it's very similar to this first step. Okay, and the third property, Sn, let Sn be an increasing sequence of sets in E. Then for A in D of A, we have union n equals 1 to infinity Sn cap A is the same as union n from 1 to infinity Sn cap A. And now this is in D of A because the Sn came from E, and by the definition of E, and then this is a countable union of increasing sets. So because D of A is D system, this is an element of D of A, which is the same as to say, by the way, this here we can write S2 minus S1 is in E. Yeah, and then this is the same as to say union n equals 1 to infinity Sn is in E again. So now the three properties of D systems are satisfied for E. So E is a D system. Okay, so this was simple because it was exactly the same strategy as for D. What we have to show is that E is not only a D system, but is equal to the D system generated by A. But now we use the claim that we've shown earlier. So E is a D system, and by the claim we know that A is a subset of E. Now the claim is gone, but if you look at the claim, then you realize that the claim says exactly that A is a subset of the set E. If you look at the definition of E and at the claim, then the claim says exactly this. Okay, so E is a D system and A is a subset of E. So so E contains D of A, right? Because D of A is the smallest D system that contains A. But now by definition of E, E was a subset of D of A, so E has to be equal to D of A. And this concludes the proof, because we noted earlier that E equal to D of A was the only thing we had to prove the lemma. Okay. So now we've shown that if we start with a pi system and then take the D system generated by it, then the result is still a pi system. Are there any questions before I erase everything?
How do you know that D of A is equal to sigma of A?
Yeah, I'll explain. So first, D of A is the intersection of all D systems that contain A, right? And we know that every sigma algebra is also a D system. Right?
Is there not too many set brackets going on? Like, it's the intersection of D systems, not sets of D systems, right?
Maybe. I'd have to say I'm blind at the moment. I mean, we can write it like this if you want. Okay, every sigma algebra is a D system. So every sigma algebra is a D system, so in other words, there are fewer sigma algebras than there are D systems, right? So this intersection over all D systems, I'm taking an intersection over more sets than if I took the intersection over all sigma algebras containing A. So let me compare this to sigma of A. Sigma of A is defined to be this intersection, and in this first intersection, I'm just taking the intersection over more sets because every sigma algebra is a D system, but not every D system is a sigma algebra. So this set can only be smaller than this set. Does that make sense?
Could you say it again?
Yes. So in this first intersection, I'm taking the intersection over more sets. So it can only become smaller and smaller. Here I'm taking the intersection over not as many sets, because every sigma algebra is a D system, but not every D system is a sigma algebra. So this can only be smaller than this, right? So this implies that D of A is a subset of sigma of A. So this is one direction. And then in the lemma we had one part of the lemma said that if A is a pi system, then D of A is a sigma algebra. Now if D of A is a sigma algebra, then it has to be, yes, that's the right word on. Then it has to be then it has to contain the sigma algebra generated by A, because the sigma algebra generated by A is the smallest sigma algebra containing A. So from this, you get the other inclusion. Was that clear? Okay. Yeah, so this is why if a D system is also a sigma algebra, the D system generated by a set is also a sigma algebra, then that D system is the same as the sigma algebra generated by that set. Any more questions? If there are no more questions, then let's prove the next lemma. So the next lemma really answers the question that I posed at the beginning of this lecture. Namely, if we have two measures which agree on a collection of subsets A, then are they equal on the sigma algebra generated by A or not? And that's why this is called uniqueness lemma. And the statement is this: let X be a set and A be a pi system on X, and denote let sigma be the sigma algebra generated by A, then let mu1, mu2 be measures on sigma such that the following holds. First, mu1 of X is equal to mu2 of X, and second, mu1 of A is equal to mu2 of A for all A in A. Right, so these two measures agree on A, and in addition, mu1 of X is equal to mu2 of X. Then we can conclude that mu1 of S is equal to mu2 of S for every S in sigma. Okay, so loosely speaking, if two measures agree on a pi system, then they also agree on the sigma algebra generated by that pi system. If, in addition, they're equal on the whole set X. So this is a really nice result, and you will see applications of this in the exercises on sheet 9 already. So this means if we have two measures, then if we want to test whether these measures are equal or not, we don't have to test them on the entire sigma algebra. We just have to test them on a pi system that generates the sigma algebra. So we can take much fewer sets, and we can already conclude that these measures are equal. Okay, and the proof of this lemma, the strategy is similar to the proof of the previous lemma, but the proof itself is a little simpler. So we start again by defining a set called D, which is defined as S or S in sigma, such that mu1 of S is equal to mu2 of S. Of course, by definition, this is a subset of sigma, right? Because it's all elements of sigma that satisfy a certain condition. And now we claim that D is a D system. And to prove the claim, again, we have to check the three properties of D systems. The first one being that X has to be an element of D. X being an element of D means that mu1 of X is equal to mu2 of X, right? But that's true by assumption. So X in D, that's clear. Second, we have to show that the difference between two sets of D is in D again. More precisely, if A and B are in D, and A is a subset of B, then B minus A has to be an element of D again. Oh, I forgot one important assumption. In this theorem, mu1 of X and mu2 of X have to be equal, and they both have to be finite. Sorry, this is important. Because that's what we're using now. So we have to look at the difference B minus A. So mu1 of B minus A has to be equal to mu2 of B minus A, and then B minus A is in D. Okay, but because mu1 and mu2 are measures, we know that mu1 of B minus A is the same as mu1 of B minus mu1 of A. But this inequality is only true because mu1 is a finite measure, right? Because this formula where you had the minus on one side, that was only true if the measure was finite. Or at least I think the measure of A had to be finite. So this is because mu1 of X is finite. Okay, but now we know A and B are in D, so mu1 of B is equal to mu2 of B, and mu1 of A is equal to mu2 of A. So this is equal to mu2 of B minus mu2 of A. And now we use this formula again to conclude that this is equal to mu2 of B minus A. And of course, in this last inequality, we've used that mu2 of X is finite. Okay, so mu1 of B minus A is equal to mu2 of B minus A. So B minus A is in D. third property we have to check is if we take an increasing sequence as n in D then we have to compare mu1 and mu2 on the union of all the Sn. So mu1 of union n equals 1 to infinity Sn. Now, because the Sn are increasing, we can use the monotone convergence theorem for sets. And then this is equal to limit n to infinity mu1 of Sn. And now, because mu1 and mu2 agree on every individual Sn, I can replace mu1 by mu2. And now the monotone convergence theorem for sets again. This is mu2 of union Sn. So mu1 and mu2 agree on the union of all the Sn, which means union Sn is in D. Okay, so this proves the claim. D is a D system. Now what do we do with that? Well, so D is a D system, and A is a subset of D. Why is A a subset of D? Because we assumed that mu1 and mu2 agree on A. So D is a D system, A is a subset of D by hypothesis. So D of A is a subset of D. Okay, so this followed from D being a D system. And now we use Dynkin's lemma. We can apply Dynkin's lemma because A was assumed to be a pi system, right? So Dynkin's lemma tells us that the D system generated by A is again a pi system, and in particular, the D system generated by A is equal to the sigma algebra generated by A. So Dynkin's lemma tells us that D of A is equal to sigma of A. But D of A was a subset of D, so sigma of A is a subset of D. Okay, and by our notation, capital sigma was equal to sigma of A. And by definition of D, D was a subset of sigma of A. Right, so we have sigma of A is a subset of D, D is a subset of sigma of A. So D is equal to sigma of A. And by the definition of D, this means that mu1 and mu2 agree on sigma of A. And this is precisely the statement of the uniqueness lemma. Okay, so you just play around with these properties of D systems and pi systems, and suddenly you have this statement about uniqueness of measures, which is quite neat. Are there any questions about this proof? Okay, we have a couple more minutes. That's just enough for... I'll leave the statement on the blackboard maybe. So that's just enough for one example and one remark. We can take all the open subintervals of the interval from 0 to 1. Then that's a pi system, right? If we take the intersection of two open subintervals of this, then that's again an open subinterval of this. Maybe to be absolutely safe, let's add the empty set. Then that's certainly a pi system. Okay, and also, so this is a pi system. And the sigma algebra generated by A is the Borel sigma algebra of the interval 0 to 1, right? We've seen that the Borel sigma algebra is generated by open intervals. Okay, so now immediately from this uniqueness lemma, we get the following statement. By the uniqueness lemma, the Lebesgue measure on this Borel sigma algebra is the only measure on Borel sigma algebra of 0, 1 satisfying mu of interval from A to B is B minus A. Right? This is an immediate consequence of the uniqueness lemma. This set of open subintervals is a pi system, so and the Lebesgue measure satisfies this formula for every open interval. So if we have any other measure that satisfies the same formula on all the open intervals, then by the uniqueness lemma it has to agree with the Lebesgue measure on the Borel sigma algebra. So this is quite a strong statement, I think. Because we started defining the Lebesgue measure by taking little boxes and